Hello, I'm Marcos Lupión, and I will present the work entitled Accelerating Peak-to-Peak Training Using a Multi-GPU Node. This is the outline we are going to follow during the presentation. As introduction, generative adversarial neural networks involves simultaneous training of two networks where one generates fake images and the other discriminates whether or not it is real in an adversarial process. On the one hand, the network called generative model generates fake data with the aim of being similar to real data. On the other hand, the network called discriminator network distinguishes real data from fake data. An adversarial training process takes place where the discriminator loss functions enhances the learning of the generator during training to achieve an equilibrium between the two. There are a lot of useful applications of GANs. In this slide, we show some of them. Conditional generative adversarial networks are a type of GAN whose input is conditioned by the user, and the output depends on this input. An application where conditional GANs are applied is image-to-image translation. In this type of problem, the end goal is the transformation of an image from one domain to the corresponding image in another domain. In the solution proposed by Philip Isola called Peaks-to-Peaks, this transformation is done having paired images from both domains. In another work, we adapt the peak-to-peak solution in order to transfer phase images from thermal domain to visible spectrum domain. Here, the diagram of different elements is shown. These elements are the inputs, where we have the person ID, the thermal image, and the visible spectrum image. The networks, where we have the generator, which transforms thermal to visible images. Face recognizer, which tries to identify the person generated from the generator. And discriminator, which discriminates from image generated by the generator or image in dataset. Also, we have some loss function which calculates errors on generator and face recognition. However, in this type of problem, there are several drawbacks that can make the training a difficult task. They are time-consuming as the training involves three networks, two backpropagation and three loss function. Therefore, the main goal of this work is to accelerate the training. In addition, it is not defined when to stop training, so the task becomes supervised and the user has to decide when to stop training. In this work, we also define a stopping method to stop once the model doesn't improve the generation of images. In this section, we'll describe the early stopping method. There are several concepts that define our early stopping method. As in the default neural network training, dataset is divided in train and evaluation. We also define metrics to monitorize during training, mean square error, and also some metrics called image quality metrics, which compare between the generated image from the generator and the corresponding ground truth visible spectrum image. In order to monitorize metrics at the end of the epochs, a caret callback is defined. This callback generates visible spectrum image from validation images and also calculates image quality metrics. Here we can see the evolution of peak signal noise ratio metric on validation data with different configurations. Results are similar in both configurations, however, batch site 8 starts producing bad results at epoch 300 more or less. So our approach lets compare between configuration and decide which one is the best. In addition, it stops when start producing bad results. The early stopping method has several key points. The metric to monitorize is peak signal noise ratio validation data. It calculates the moving average on peak signal noise ratio to smooth the data, and also the stopping method occurs when peak signal noise ratio doesn't improve after 50 epochs. Here we can see the evolution of phase transformation in a use case of 3000 epochs. In the epoch 405, we can see the best transformation. In other epochs, there can be similar peak signal noise ratio values, but the transformation don't improve. In this section, we'll describe the 5 optimizations incorporated into the system. A very important factor in neural network training is the batch size. It is the number of images that are processed before update the model weights. In the official paper, there are two approaches. First, when there are lower than 3,000 images, the batch size is set to 1. Second, when there are more than 3,000 images, the batch size is set to 4. In our dataset, there are 2,160 images, so the configuration will be a batch size of 1. However, increasing the batch size improves the default configuration. After several configurations, there are some batch sizes that improve the configuration defined in the original work. The best configuration is a batch size of 64, stopping trailing in epoch number 385. The epoch stop will vary in different training. Here, the images corresponding to each batch size are shown. When increasing the batch size, more images has to be processed to produce a model update. Therefore, in literature, it is reported that when increasing the batch size, it's necessary to increase the learning rate. Several authors propose multiply the learning rate by the root of the increase in batch size, or directly multiply by this increase. However, in our problem, applying these changes don't improve the default training, as we can see in the orange line. The multiplication approach, which is the gray line, is too aggressive, producing bad results after 30 epochs, and the lowest value on peak signal noise ratio. The root square approach, which is the blue line, is similar than the default configuration, achieving 1793, but after 150 epochs, it starts generating bad results. In third place, a very important process when training neural network on GPUs is loading them into the GPUs. By default, the CPU has to pre-process the images, resize, and generate tensor before loading them into the GPU, wasting some processing time as they remain in use. In our work, we incorporate the cache usage in order to store the pre-processed images by the CPU only one time, not at all epochs. In addition, images are prefetched in GPU in order to avoid any waiting time on them. Using the TensorFlow profiler, the time spent on the input pipeline can be appreciated. In the left image, the default configuration is shown. We can appreciate approximately 30 milliseconds are spent in the input pipeline. In pink color, we can see it. While in the optimized configuration, no time is appreciated. Therefore, the GPU doesn't have to wait to the CPU to load images, accelerating the training process. In fourth place, another optimization is carried out by introducing the mixed precision. This is a feature which is exploited by some type of GPUs like NVIDIA Volta architecture. They incorporate tensor cores, being able to multiply the speed of processing mixed precision data. Including this computation, the operations are done in 16 bits floating point numbers, and the model weights are stored in full precision format. Using mixed precision, the memory needed to process data is reduced a half. It's mandatory to incorporate some scaling function which scale losses in order very small values do not overflow. In fifth place, we present the most important optimization, the multi-GPU approach. This approach, there are two types of parallelism, data and model parallelism. In the first one, the batch is divided in both GPUs. After each GPU processes the data, a reduction operation is carried out that generates the loss of the whole batch. In model parallelism, the model is divided and distributed in different GPUs. Once the batch of data is processed in a GPU, the result goes to the next GPU. Only in this case, the data parallelism is currently supported by TensorFlow, so we use this approach. When using multiple GPUs, we only have to modify the loss function on the system, as the reduction operation can be made by default by TensorFlow. In this slide, we show the first loss function which has to be adapted. It is the function which calculates the adversarial error defined in GANs. The result of each image is a 30x30 matrix where the discriminator decides if each batch of generated image is true or false. As said before, the single GPU approach calculates the general loss value using a default reduction operation. In multi-GPU, each GPU calculates the loss of its own batch size of 4 in this case. However, this loss has to be calculated manually. In each GPU, the operation is the addition of all losses of all images in batch and then divided by the dimension and batch size. Finally, the compute losses of each batch are added to calculate the general loss. In face recognition loss, the sparse categorical cross entropy gives a value from each image. When using a multi-GPU approach, the aggregation operation adds all losses in batch size and divides by the total batch size. This is the operation suggested by TensorFlow documentation, which is possible when having only zero-dimensional tensor, as we have here. In the following section, the results of the different optimizations are going to be shown. First, when applying the input pipeline optimization, a small acceleration of process is carried out. We notice that this optimization is greater when the batch size is increased. In the two GPUs approach, the optimization is lower than the single GPU due to the synchronization between GPUs and CPUs. Second, misprecision produces a greater acceleration until arriving into 1.9 speedup. Third, the final version having the input pipeline optimization and the misprecision increase until 2 the speedup. The best optimization occurs when batch size is 64. Here, the evolution of epoch training time using 1 and 2 GPUs is shown. Using a single GPU approach, when arriving to batch size 128 and 256, there are some out-of-memory problems. Only the mixed precision configuration lets finish training on batch size 256. When using a system with two GPUs, the best configuration is also batch size 64. Only the mixed precision and optimized configuration give results when batch size is 256. In default and input pipeline configuration, there are also some out-of-memory problems. In this slide, the speedup between single and multi-GPU approach is shown. The maximum speedup is 1.92 between single and two GPUs approach. It takes place at epoch 64. The ideal speedup will be 2 in this case. Comparing to the configuration having batch size 1 and single GPU, the two GPUs approach with the optimization has a speedup of 7.08. As conclusion, an early stopping method using peak signal noise ratio and validation data has been incorporated in peak-to-peak GANs. This method lets stop the system when results are achieved. An early stopping method using peak signal noise ratio and validation data has been incorporated in peak-to-peak GANs. This method lets stop the system when best results are achieved. The input pipeline of the original work has been improved using the cache and prefetching data in GPU. System is also adapted to support misprecision operation, which accelerates training using tensor cores on NVIDIA Volta GPUs. Increasing the batch size with respect to the original work improves the image transformation, while allowing for faster training. In our work, the batch size 64 is the best configuration. The system is adapted to support multi-GPU training, and the loss function is a very key factor when adapting to multi-GPU. So tests using two GPUs has been included, achieving a speedup of 1.92. Comparing to the configuration in original paper, our training has a speedup of 7.08. As far as future work is concerned, in order to increase the level of parallelism, more GPUs will be added. This is the final of my presentation. Thank you for your attention. I'm very pleased to answer your questions.